Welcome to problem solving session number 4. In this problem solving session, we are going to solve problems on the squeeze states, coherent states, and even quantization of electromagnetic fields. Most of the problems I have picked up from the classic book, The Quantum Theory of Light by Rudley Loudon. So let us solve the first problem. A operator relation is given, and this relation is valid provided the operators C and D satisfy these commutation relations, and using it also with the vacuum state condition. That means when an annihilation operator operates on the vacuum, you know that you get 0. Then you have to cast this well-known equation for the coherent state. This relation is already all of us know. This relation we have to put it in the form like this. Okay, let us do it. First of all, let me choose operator C and D appropriately. Let me take C to be equal to, say, alpha A dagger and D to be minus alpha star A. Let us first check whether this choice is alright or not. To do that, we have to show that this relation C C should commute with the commutator CD, right? And so let us find it out first. Before I do this, let me find out what is CD, commutation relation between C and D. That would be alpha A dagger here. D is equal to alpha star A, and this I can write as minus mod alpha square. Then I have A dagger A, and A dagger A is equal to minus 1 because A dagger is equal to 1. So I will have simply mod alpha square. Okay, so here therefore I have C is equal to alpha A dagger and commutator CD is equal to mod alpha square, which is just a number, so therefore it is equal to 0. So similarly we can actually prove in the similar way that D commutes with the commutator CD. So therefore our choice is perfect. C and D is alright. So therefore we can apply the formula. So e to the power alpha A dagger e to the power minus alpha star A, this formula, right? Now I'm going to apply this formula. So therefore this would be equal to e to the power alpha A dagger minus alpha star A plus half of the commutator alpha A dagger minus alpha star A, and this we can have already, we have worked this part. So therefore, and that is equal to mod alpha square. So therefore I can write it as e to the power alpha A dagger minus alpha star A plus half of mod alpha square, and using this I can therefore write this part. I can write it as e to the power alpha A dagger minus alpha star A is equal to e to the power alpha A dagger. I am taking this part to the left hand side. Then I will have e to the power alpha. If I take it to this side, then I have e to the power alpha A dagger minus half of mod alpha square, and I have e to the power minus alpha star A. Okay, now if I operate e to the power alpha star A, I am talking about this part. if it operates on the vacuum state, I can expand this into this series like this: 1 minus alpha star A plus alpha star square by 2 factorial A square and so on. If it operates on 0 vacuum state, you know that when annihilation operator operates on the vacuum state, we will get 0. So all the other terms will be 0, so we will be left out with only this. So this would be equal to simply the vacuum state 0. So therefore, so I can just write that very trivially. I can write e to the power alpha A dagger minus alpha star A when it operates on the vacuum state. So this is what I'm writing here. If it operates on this, then you will be left out with e to the power alpha A dagger minus half mod alpha square. Okay, this operating on this kth 0, and we know that this is nothing but your kth alpha, as already you can see it from here. Okay, so this is your kth alpha, and therefore we have written it in the required form. So it implies that we have kth alpha is equal to exponential alpha A dagger minus alpha star A kth 0. Now let us work out this problem. This is actually related to operator algebra. So we have to prove this relation. It's looking very complicated, but let us see. We know that when the annihilation operator operates on the number state, this relation is already, you know, that would be square root of n and n minus 1 kth. And if the creation operator operates on the number state, we'll get square root of n plus 1 and kth n plus 1. So we have to utilize this relation. So let us look at this relation first. If we now apply annihilation operator on A dagger n, which would be A square root of n plus 1 kth, and this we'll get it as n plus 1 kth n. Again, if I apply it by A operator, annihilation operator on the whole thing, then I will get n plus 1 square root of n minus 1 and so on. Actually, we can now repeat this application of these rules for the sequence of these operators, and I encourage you to do it. You will get A dagger cube A to the power 4 A dagger n. If you work it out, you should get n plus 1 n into n minus 1 n minus 2 kth n. So let me say this is my equation number 1, and from here immediately, okay, let me say, if I now multiply on the left hand side by bra n, then I will get simply n plus 1 into n minus 1 n minus 2. Okay, so this is what I will get. So we have basically worked out this part. Now what about this again? Let us work that out. In the similar fashion, we can actually work it out. And if we work it out, do the algebra. It's straightforward algebra, but little bit tedious. A dagger 4 A, and if you work it out, let me see whether I'm writing. Yeah, this is what I have here. If you work it out, you will get n plus 3, n plus 2, n plus 1, n, and from here, if I multiply it by bra n, then I will get a cube, a to the power, a dagger to the power 4, a n, that would be equal to n plus 3, n plus 2, n plus 1 into n, because we know that this is equal to 1, right? Okay, let us say this is my equation number 2. Now if I compare equation number 1 and 2, you will see that n plus 1 into n is common to both. So if they have to be equal, so I have to multiply equation 1 by this one and multiply equation 2 with, say, this one. Okay, if I do that, you will see I will get n plus 3 into n plus 2, so bra n, a dagger cube, a to the power 4, a dagger n, that is going to be equal to, so on the other side here, just this one, that would be equal if I multiply this as n minus 1 into n minus 2, and I will have n a cube, a dagger to the power 4, a n. So I think this is what is asked in the question, and we have proved it. Now let us work out this particular problem. Here you are asked to prove this commutation relation, and then for the general case where n is an positive integer, this is what you have to prove, and finally you are asked to establish this commutation relation. So let us do that. It is related to operator algebra. So first one, this is simple. A dagger square, the commutation relation we have to work out. So we can write it as a dagger, a dagger plus a dagger, a dagger. Now we know that a dagger is equal to 1, so therefore we will have a dagger plus a dagger, so therefore this has to be 2a dagger. Okay, so this one is proved. Similarly, the second one also we can prove. Here we have a square, a dagger, that we can write as a dagger plus a dagger a, and again because a dagger, this commutation is equal to 1, this is equal to 1, so we will have 2a, not a dagger, 2a. So this is also proved. Now we have to find out this general relation where a dagger to the power n, where n is a positive integer. So what is this? So let us proceed as follows. First of all, we notice that, which already we have proved, a dagger square is equal to 2a dagger. Now let us work out a dagger cube. This we can write it as a cube. There are 3a daggers, multiplication is there, and these are operators, so order matters. This one I can write it as a dagger, a a dagger square plus a dagger a dagger, and already we have worked it out, and this guy is 2a dagger, right? So therefore we will have here twice of a dagger square, and here we have a dagger is equal to 1, so therefore we will have a dagger square, so this will give us 3a dagger square. So we have a dagger cube is equal to 3a dagger square. Let us do another one. We have, say, a dagger to the power 4. What about this? Again, in the similar way, we can write it as a. You have 4a dagger that's are multiplied, and this we can write as a dagger a dagger to the power 3, and here I can write it as a dagger and a dagger cube, and a dagger cube already we have worked out from here, so we'll have 3a dagger to the power 4, and a dagger is equal to 1, so this would be 3a dagger square, so it is cube, and here we have a dagger cube, so this will be 4a dagger cube. So as you can see from here, okay, if you examine all these relations, so this way you can go on, and therefore I can conclude that a dagger to the power n would be equal to n a dagger to the power n minus 1. Okay, similarly you can prove applying the same procedure, a dagger to the power n a dagger, this commutation relation you can prove it to be n a dagger a to the power n minus 1. Okay, finally we are asked to establish the relationship. We know what is this commutation relation is given, and we are asked to prove a with e to the power beta a dagger. So what is this? We have to prove e to the power beta a dagger. We can write it as 1 plus beta a dagger plus half beta a dagger whole square plus 1 by 3 factorial beta a dagger cube, and so on. Therefore the commutation a e to the power beta a dagger, this we can write as a, I have here 1 plus beta a dagger plus a half beta square a dagger square plus 1 by 6 beta cube a dagger cube, and so on. So which I can write as a1 plus a beta a dagger a half beta square a dagger square, and so on. So first of all, this is a number, so this commutation relation will give me 0, plus this one will have beta into a dagger, so it would be simply beta, the second one. Okay, and the third one I can have half beta square a dagger square, commutation between a dagger square, which already we know that would be twice of a dagger, and then I think we'll have again 1 by 6 beta cube a dagger cube. So what we'll have here is beta plus beta square a dagger. Then we'll have a dagger cube, that would be 3 a dagger square. So therefore I will have here a half beta cube a dagger square, and this I can now write as beta 1 plus beta a dagger plus a half beta a dagger whole square. Okay, and therefore this expression I can write as e to the power beta a dagger. So this is what was asked to prove. Let us see. Yes, so therefore we have proved this relation. Okay, now let us work out this particular problem where you are asked to prove the commutation relation between the Hamiltonian of the electromagnetic field and its vector potential. Let us work it out. Before I do that, let me remind you about the operator form of various quantities. For example, the electric field operator for a traveling electromagnetic wave, which we have done in our class, in our lecture, as this. So I h cross omega divided by twice epsilon 0 v square root. It is propagating along, say, it is electric field direction is, say, eta, and we have a e to the power I k dot r minus a dagger e to the power minus I k dot r. So that is the electric field. And the magnetic field, we know the expression was I into h cross divided by twice epsilon 0 v omega square root k cross eta, and we had a e to the power I k dot r minus a dagger e to the power minus I k dot r. We have not worked out the expression for the vector potential, but vector potential can also be very easily worked out, and in fact I urge you to verify it. You will find that the expression for the vector potential would be of this type. It would be h cross divided by twice epsilon 0 v omega square root eta vector, then a e to the power I k dot r plus a dagger e to the power minus I k dot r. So these are our required expressions. In fact, you can verify that this expression is alright for the vector potential if you, because you know that under Coulomb gauge we wrote our electric field operator as its time derivative of the vector potential, and while verifying it you just always keep in mind that this annihilation operator varies in time as a e to the power minus I omega t. If you keep these things in mind, and if you put it in this expression, you will be able to get the expression for the electric field. Okay, so please try to verify it. Now let me proceed with the given problem. So here we are asked to find out the commutation relation between the Hamiltonian and the vector potential. So we have the Hamiltonian is h cross omega a dagger a. I'm doing it for single mode, but this can easily be done for multi-mode case also. So here this is the Hamiltonian, and the vector potential, let me write down the full expression, h cross divided by twice epsilon 0 v omega eta vector, and I have a e to the power I k dot r plus a dagger e to the power minus I k dot r. Okay, actually if you see it, essentially this problem is to just to find out the commutation relation between a dagger a and a, and also this one with this, and then this one with this one. So therefore we have to just find out these two expression, and then you'll be able to work it out very simply. So this one a dagger a, so this would be equal to a dagger a plus I can write it as a dagger a, which is obviously 0, so let us not bother about it. So this will simply give us minus a, and similarly here I will get it as a dagger a dagger, and this will give me plus a dagger. Okay, this is what I will have. Therefore I can have the commutation relation between the Hamiltonian and the vector potential would be equal to, I can just take these things out, h cross omega I can take out. Okay, let us do it. So h cross we'll have h cross omega here, h cross divided by twice epsilon 0 v omega under root, and this eta vector. Then I have here I have already know these two relationships, so I have to utilize it here. Then you will see that I will get here minus a e to the power I k dot r from the first term, and from the second one I will get a dagger e to the power minus I k dot r. Okay, so I have, then I can write it as minus h cross omega, let me take inside, h cross omega twice epsilon 0 v under root eta vector. This I can write as a e to the power I k dot r minus a dagger e to the power minus I k dot r. So this is what I have. Now if you look at the expression for the electric field, okay, this one if you see, then you will know that I have minus h cross, and the whole this expression is electric field. I will get it, I just have to multiply it by I and divide it by I, right? So okay, so I hope you get the idea here. So this one would be minus h cross e electric field operator divided by I. This whole thing is that. Therefore I have here I h cross the electric field operator. So I think this is what was asked to prove. Yes, indeed. So therefore the commutation relation between the Hamiltonian and the vector potential is this. So what it means physically is that the energy operator for the electromagnetic field and the vector potential do not commute. Okay, let us now work out this problem. You are asked to derive this transformation property for this squeezing operator. In fact, we have discussed it in the class but did not prove it. So let us prove it. Here we know that we have taken our squeezing operator as xi as e to the power half xi a dagger square minus half xi star a square. Then s dagger xi would be equal to e to the power half xi star a square minus half xi a dagger square. Now we have to simplify s dagger xi A as xi. So going by this formula, given formula, let us take the operator A to be the small a, annihilation operator, and B, let me take it as a half xi a dagger square minus half xi star a square. Then we have this formula, e to the power minus b a e to the power b, that is equal to a plus ab plus 1 by 2 factorial ab commutator, then b, then we'll have term like 1 by 3 factorial. I'll have a b b b here. Okay, like this. Let us evaluate term by term. First of all, if I evaluate AB, this I will have capital A is equal to the small a, and B is equal to half xi a dagger square minus half xi star a square, because a commutes with a square, so we need not have to bother that part, so we have to bother about this part. So this I can write as half xi a dagger square, which we know that this would be half xi, and this is 2a dagger, so therefore this would be simply xi a dagger. Now next term, we have AB, this commutator with B. Let us evaluate it, and this would be xi a dagger, and B is half xi a dagger square minus half xi star a square. Again, we have to bother about a dagger and a square, this part only, because a dagger and a dagger square will commute. So this I can write as minus half, let me take this side, and xi into xi star, so that would be mod xi square, and we'll have a dagger a square. Okay, this you can work out. This would be minus half xi square, so here I can write it as a dagger a plus a dagger a dagger a is equal to minus 1, similarly here, so therefore I will have it as simply a mod xi square. Okay, so let me work out another term, that would be, say, AB commutator with B. This already we know, this commutator of this whole thing with the operator B. Let us work it out. This would be a mod xi square, and then here I have B is half xi a dagger square minus half xi star a square. Okay, so I will get here it as a half mod xi square xi a dagger square, and this will give me mod xi square xi a dagger. Okay, so now let us gather all the terms. S dagger xi a as xi. So if I gather the terms, first term is a, the second term is xi a dagger, third term is 1 by 2 factorial a mod xi square, fourth term would be 1 by 3 factorial mod xi square xi a dagger, plus like this. So we'll have various terms. Now if I take a common, then I have 1 plus 1 by 2 factorial mod xi square. I will get an idea about the series basically here, and I will have a dagger. If I take common, then I have xi plus 1 by 3 factorial mod xi square xi, in terms like this. So I know that xi is equal to, it's a complex quantity, that would be mod xi, which is actually r. Xi is equal to r e to the power I theta. So mod xi is equal to r. So therefore I can write a 1 plus 1 by 2 factorial r square and so on. And here I'll have a dagger e to the power I theta r plus 1 by 3 factorial r cube and so on. So you can immediately recognize that here I have a cos hyperbolic r, and here I have a dagger e to the power I theta sine hyperbolic r. So hence we have proved the relation.